Enterprise modernization commands massive capital allocation. Entire legacy systems, handling billions in transactions, are targeted for replacement before their infrastructure starts grinding to a halt. When executives approve these initiatives, they treat them strictly as capital investments. The baseline expectation from the CFO is a clear, predictable return on investment, typically modeled within a 24 to 36-month window. Yet, the vast majority of these capital-intensive projects fail to deliver on those financial promises. This creates the ROI illusion. Initial cost projections look sound on paper, but actual execution costs wildly diverge. The trajectory flatlines because projects are approved on financial terms, but delivery teams track progress through technical milestones. Hitting a milestone for migrated code or achieving target cloud uptime does not automatically reduce operational costs or accelerate revenue generation. Measuring technical outputs while expecting financial outcomes guarantees project underperformance. The two metrics operate completely independent of each other. The root cause lies within the legacy monoliths themselves. After decades of patches, these systems become deeply entangled and nearly impossible to map. This creates the visibility gap. Critical business logic remains undocumented, buried deep within the architecture, making it impossible to accurately scope the required effort. Moving forward without clear system documentation forces delivery teams into a reactive posture. They are forced to conduct endless, unplanned discovery cycles right in the middle of active execution. As teams unearth unexpected dependencies, the sheer volume of required labor spikes. The budget bloats instantly to accommodate the newfound complexity. Every prolonged discovery cycle stretches the execution timeline further out. The 24-month break-even point slips to 36 months, then 48, completely destroying the project's capital efficiency. This chaotic, discovery-driven execution model stands in direct opposition to the CFO's absolute mandate. Financial stakeholders require rigid cost predictability and strictly bounded project scopes. To protect allocated capital and secure the ROI, engineering teams must achieve total systemic visibility before migrating a single line of code. Relying on manual discovery completely underestimates the true density of heavily patched legacy environments. Humans simply cannot track every hidden connection. A common trap occurs when delivery teams isolate a specific module for migration. They falsely assume the code operates independently of the wider system. This is a hub-and-spoke diagram mapping the dependencies for a mainframe modernization project. AI-driven mapping reveals the hidden architecture of the environment before any structural errors are made. Looking at the central hub, we can identify how core applications are tightly tethered to dozens of undocumented external processes. A minor peripheral change directly impacts critical upstream data utilities, systems the modernization team might not even know exist. Modifying that single peripheral without understanding the map breaks the central system. The project grinds to a halt while engineers enter emergency triage. Generating this exact topology automatically via AI eliminates the need for manual, error-prone discovery phases. Automated dependency extraction converts modernization from an open-ended exploration into a strictly bounded, highly predictable scope of work. Zooming in from the systemic level, we can see how even routine regulatory changes initiate modernization tasks with hidden risks. Take a highly specific, real-world scenario. Expanding a Brazilian tax ID from a 14-character numeric field to an alphanumeric string to comply with a new standard. In a traditional execution model, an engineer updates the database field to accept letters. They push the update, completely blind to how that data is digested later in the workflow. The result is a production crash. Downstream extraction programs ingest the unexpected alphanumeric data, fail the validation check, and take the system offline. This interface shows an AI impact analysis designed to mathematically trace a single variable's path across the entire monolithic codebase. The system first parses the existing environment, identifying the exact parameters of the current state field within the ADABAS file, specifically noting its numeric-only restriction. It then traces that variable directly into downstream COBOL reporting programs that rely on those numeric constraints to function. Understanding this exact blast radius allows project managers to correctly estimate the required labor, time, and budget upfront. Neutralizing late-stage rework through static analysis is the most effective lever for preventing budget overruns and preserving executive confidence. This lack of visibility feeds directly into a severe structural labor constraint. Modernizing legacy systems relies entirely on a shrinking pool of highly expensive legacy specialists. Concentrating institutional knowledge in a few specialized engineers creates immediate bottlenecks. Delivery velocity plummets, artificially inflating the capital expenditure of the project. To bypass this constraint, teams must decouple the company's core business intent from the outdated proprietary syntax it is written in. This document outlines extracted business logic sitting next to its corresponding pseudocode block. Large language models analyze millions of lines of monolith code to isolate the pure business rules. Complex programmatic syntax is translated seamlessly into highly readable, universally understood instructions. Democratizing this logic allows broader, modern engineering teams to architect the future state safely without needing decades of mainframe experience. This table shows the direct, deterministic mapping from legacy CICS transactions directly to modern Spring Boot REST endpoints. AI-driven logic extraction solves the labor cost crisis, transforming how human capital is deployed to maximize the return on the investment. The ultimate objective is clear: moving from a fragile, tangled legacy architecture to a pristine, modular, modern environment. This flowchart outlines the recommended target architecture for a finalized mainframe migration. We can see the clean divisions between client interfaces, API gateways, and granular transaction microservices. Achieving this pristine architecture is financially meaningless if the execution journey destroys the budget along the way. When we apply AI-augmented methodologies, the trajectory of capital expenditure changes entirely. Utilizing AI mapping creates a slightly steeper initial cost due to the rigorous upfront discovery investment, but eliminating unknowns early results in a hyperlinear execution phase, hitting profitability targets precisely on time. Platforms executing this determinism actively bridge the gap between complex engineering reality and strict executive mandates. When engineering teams operate with predictability, they stop acting as volatile cost centers and become strategic value drivers for the enterprise. If you cannot mathematically predict the complexity of a system, you cannot predict its cost. Technical visibility is the ultimate prerequisite for financial success.